Hello, welcome to a new lesson of differential equations. Today we are going to continue talking about the Sturm-Liouville problem, and we are going to introduce the Sturm-Liouville operator. So we are interested in this topic because it can be very related with the green function. Okay, so we are going to make another lesson where we talk about how to introduce the green function in the Sturm-Liouville problem. Okay, so for now, let me define what is this Sturm-Liouville operator? So we are going to name it with the letter L, this curly L, and it can be defined as a 1 divided by W of x times the derivative with respect to x of P of x, the derivative with respect to x, and then plus Q of x, like this. Okay, so this is just the definition of the operator. So let me write this. And what we can do with this is to construct the Sturm-Liouville differential equation that we have shown in previous lessons, just by saying that the Sturm-Liouville operator can be applied to a function y of x, and it will be equal to minus lambda y of x. Okay, so with this we can simplify a lot, just the way we write the Sturm-Liouville differential equation. Okay, so just to show you that this is exactly the same that we have been working with, we can, for example, substitute the value of the operator here to get that this is going to be the derivative with respect to x of p of x, the derivative of y with respect to x, plus q of x times y of x, all divided by 1, well, divided by w of x, of course, and this will be plus lambda y of x equals to 0. If we multiply all this equation by w of x, we will get the structure of the differential equation that we have been working with on the first videos that we made about the Sturm-Liouville problem. So we are going to be interested in showing that this operator is actually Hermitian. Okay, it's an important property of the Sturm-Liouville operator, and that is what we are going to do in this video. Another thing that it is important to mention is that this operator is defined on an interval a comma b for x, and these functions w, p, q, and p prime are real functions that are continuous in this interval. Okay, real continuous functions. So this is going to be important. Perfect. So another thing that we need to define first to show that this L is Hermitian is that we are going to use the bracket notation that is very common in quantum mechanics, but in this case it's just to make things simpler. So we are going to say that a function f, for example, we are going to see it as a vector or a ket like this. And for example, if we have a function g, well, this can be seen as the ket g. Okay, perfect. So with this, we can introduce the concept of the brass, right? So for example, we are going to say that g conjugate can be seen as the bra g like this. And then f conjugate is going to be, well, the bra f. Perfect. So with this, we are going to work with the function f and g. Other thing that is important to remember that we mentioned on previous lessons is that we can define the inner product in the Sturm-Liouville problem as follows. Using this notation, it will be the inner product between f and g is going to be the integral from a to b of f conjugate times g and times the function of weight, which is w of x. Okay, this function over here. So this is how we define the inner product in the Sturm-Liouville context. Okay, perfect. So in this manner, if we apply the Sturm-Liouville operator to the ket g, well, this is just going to be the Sturm-Liouville operator applied to the function. Okay, so it will be 1 over w of x times the derivative with respect to x of p of x, the derivative of g with respect to x, plus q of x, g of x, like this. And the Sturm-Liouville operator applied to f, it will be 1 over w, and I'm going to omit writing the dependence on x all the time. So it will be 1 over w, the derivative with respect to x of p, and then f prime plus q times f, like this. So what happens if we want to calculate the inner product between f and, let's say, L applied to G? Because this can be seen as a ket, and this is other ket, right? So this will be like the ket f. So we are going to be interested in calculating the inner product between this. So that quantity will be f times Lg, like this. But looking that we are taking the bra f, we are going to introduce that f as f conjugate, right? So we need to take here the integral from a to b of f conjugate, and then L applied to g, which is this thing over here. So it will be 1 over w, the derivative with respect to x of p g prime plus q g. And then by definition, remember that the inner product has a w here and the x. So we can cancel the w's, and we get that the inner product between f and Lg is equal to the integral from a to b of f conjugate times the derivative with respect to x of pg prime plus qg dx. Okay, perfect. So something that we need to remember of the bracket notation is that if we have a, b, like this, the inner product between a and b, this is equal to ba conjugate. Okay, so this means that if we have f with Lg, this can be seen as the bra f that multiplies Lg, like this, and this should be equal to all this thing conjugate. But we need to take this as a bra, right? So it will be g, but you know that if we are taking the dual of the operator, right, applied to the bra instead of the ket, we need to take L daga. Okay, and then this is the f over here. And looking that we made the switch of the order of the g and the f, we need to take the conjugate over here. And we remember that if an operator is Hermitian, well, that means that L is equal to L daga, right? This is from linear algebra or from your basic courses on quantum mechanics. You should know this. And well, that means that F L G is equal to G L F conjugate. Okay, perfect. So what we are going to do is to calculate these two quantities, then we are going to subtract them, and if we get 0, well, that will mean that this operator L is Hermitian. Okay? So by now, we already calculated what is FLG. Okay, so we need to calculate now GLF conjugate, right? Which is this quantity over here. So what will that be? Well, again, by definition of the inner product, we will get that GLF is equal to the integral from a to b of a g, but we have the bra g, so that will be g conjugate, and then 1 divided by w, the derivative with respect to x of p, the derivative of f, right, with respect to x, then plus q times f, and then w dx. Again, we cancel the w's, and we will get that GLF conjugate is equal to, well, the conjugate of all these things, right? So here we have the integral from a to b. We take the conjugate of g conjugate, which is just g, and then the derivative with respect to x of, here remember that we mentioned that p and q are real functions. So if we take the conjugate of a real function, we will get the same real function, right? So here we just need to take the conjugate of f. So let me write this as f prime conjugate and then plus qf conjugate times dx. Okay, perfect. So from here, we can now make the subtraction of this quantity minus this other quantity that we found, and we'll see what are we going to get. It will be GLF conjugate minus FLG. Well, this will be equal to the integral from a to b of g, the derivative with respect to x of pf prime conjugate plus qf conjugate dx, and then minus, it will be minus f prime, conjugate, the derivative with respect to x, pg prime plus qg, and then all these times dx. Yeah, just to make some order here, let me erase this and put some brackets here. I'm already combining both integrals in just one. Okay, so this will be equal to the integral from a to b. We are going to develop this derivative. So this will be g times p prime f prime conjugate plus p f double prime conjugate plus q f conjugate, and then minus f conjugate times p prime g prime plus g double prime p plus qg. Okay, and yeah, here are the brackets to write the x here. Okay, perfect. So from here, we can easily see that this element can cancel with this element because we have qf conjugate g and we have qf conjugate g subtracting. Okay, so this will be equal to the integral from a to b of g times p prime f prime conjugate plus p f double prime conjugate, and then minus f conjugate p prime g prime plus g double prime p, and then dx. Okay, so from here we are going to get the integral from a to b and then g here, and remember that this element over here comes from the derivative of a product, right? It comes from developing this product over here. But I think that developing that product, maybe it was a mistake because we can see this again as the derivative with respect to x of p times f prime conjugate. And I think this will be more convenient because we are going to integrate by parts this integral. So we know that the integral of a derivative will cancel, and we are just going to get the elements that are inside the derivative. So I think it is more convenient to watch this again as the derivative of a product. And we are going to do the same thing over here. We will get minus f conjugate times the derivative with respect to x of p times g prime, like this, and dx. So what do we get if we integrate by parts this expression? Okay, we are going to name this as u, and then this, of course, as db, and it will be g times b, which is pf prime conjugate, and this goes from a to b, and then minus the integral from a to b of b times du, right? But that will be pf prime conjugate times g prime dx, of course, just by using the integration by parts formula. And then we will get here minus Then, of course, this is going to be u, this is going to be db, and we will get minus u, which is f conjugate, times b, which is pg prime from a to b, and then minus the integral from a to b of b du, right? But that is pg prime and then f conjugate prime dx. Okay, perfect. So from here, we easily notice that we have minus this integral, and then minus with this minus is a plus, and we have the same exactly integral, pg prime f prime conjugate. So this can cancel. And we are going to get g pf prime conjugate from a to b, and then minus f conjugate pg prime from a to b. So if L is Hermitian, then these two quantities are equal. And if they are equal, the subtraction is 0. And that subtraction is this expression. So if L is Hermitian, this thing is 0. So we still need to show that this thing is 0, right? Okay, so how are we going to do that? Well, from the definition of the Sturm-Liouville problem, we know that there are some boundary conditions that at the beginning of the video I should have mentioned that this differential equation is not itself the Sturm-Liouville problem. Remember, there are two boundary conditions along with this differential equation that define the whole Sturm-Liouville problem. Okay, so we are going to make use of those boundary conditions that I'm about to write here. So just thinking that f and g are functions that satisfy the Sturm-Liouville problem, well, this means that we will have two conditions for every function, two for f and two for g. Okay, so the equations for f are going to be the next. It will be alpha 1 f of a plus alpha 2 f prime of a is equal to 0. And then we will get beta, or let me write alpha 3 f of b plus alpha 4 f of b is equal to 0. Remember that a and b are the limits of the interval where the problem is defined, right? Recall that a is less than or equal to x, which is less than or equal to b. So are the extreme positions of the interval. Okay, and again, this is for f, but we have other two equations for g. So that will be beta 1 g of a, and then plus beta 2 g prime of a equal to 0, and then beta 3 g of b plus beta 4 g prime of b equals to 0. Okay, so from these four equations, we are going to be interested in this equation, and we are also going to be interested in this equation over here. So let me rewrite these two equations as a system of equations, that is alpha 1 f of a plus alpha 2 f prime of a equal to 0, and then beta 1 g of a plus beta 2 g prime of a equal to 0. So from here, we can just take the conjugate of the first equation, and recall that alpha and beta are constants that are real, okay? So if we take the conjugate of the first equation, we will get alpha 1 f conjugate of a plus alpha 2 f prime conjugate of a equals to 0, and then beta 1 g of a plus beta 2 g prime of a is equal to 0. And from basic linear algebra, we know that when a system of equations is homogeneous, recall that that means that the equations are equal to 0. Well, when that happens, just to have a non-trivial solution, we need that the determinant of the coefficients to be equal to 0. Okay, so that means that f conjugate of a, f prime conjugate of a, g of a, g prime of a is equal to 0. Okay, so if we do this, we will get f conjugate of a times g prime of a minus f prime conjugate of a times g of a is equal to 0. Okay, perfect. So if we go back to this structure that we have here, well, first I'm going to bring it back to the current page because we do not have much space here. Okay, so I just rewrote the expression that we found. So from here we can see that we have a common factor p. So we can see this as p and then g f prime conjugate from a to b minus p f conjugate g prime from a to b. Okay, and then we can see this as p of b times g of b f prime conjugate of b minus f conjugate of b g prime of b. Okay, and then it will be minus p of a times g of a f prime conjugate of a minus f conjugate of a g prime of a, like this. And we see that from this equation, this expression that we have here is exactly the same. So we can say that this is equal to 0. And, well, in this case, we just found the equation for the a, right? But if we take these two equations for b, and we make exactly the same process that we have done here and here, we are going to get that this expression is also equal to 0. Okay? So with this, we can say that this is equal to 0. Okay? So I'm going to make a quick resume of what we have done to show the objective of the lesson. From the initial conditions that define the Sturm-Liouville problem, we fix two systems of equations that, these system of equations are of this form. And if we take the determinant to be equal to 0 for having non-trivial solutions, then we can say that this property holds. But that property is equivalent to say that this thing minus this thing is equal to 0. And if this thing is equal to this thing, well, that means that L is Hermitian. Okay? So with this, we can conclude that the L operator is Hermitian. Okay, perfect. So I think that I'm still going to make a quick example of a very famous equation that can be seen as a Sturm-Liouville equation. You should know from quantum mechanics the Schrödinger equation structure, right? So we know that the Schrödinger equation is minus h bar squared over 2m, the second derivative of phi of x with respect to x. In this case, it's just in one dimension, okay? So it is plus a certain potential, which is a function of x times psi of x equals to e times psi of x. So again, this is the time-independent Schrödinger equation. So just by making some algebraic steps, we can say this as the second derivative with respect to x of psi of x minus 2m divided by h bar squared b of x psi of x equals minus 2m e divided by h bar squared psi of x. Okay? But we know that the Sturm-Liouville problem has the next structure. It is L applied to y of x equals to minus lambda y of x. So this is taking us to have that. And switching the y for the psi of x, we are going to get a 1 over w p prime, the derivative with respect to x, plus p, the second derivative with respect to x, like this, plus q times psi. This is going to be equal to 1 over w p prime, the derivative of psi with respect to x, plus p, the derivative with respect to x, the second derivative of psi, plus q psi. And looking that the Schrödinger equation does not have a first order element, we can see from here that p prime should be a constant number because, sorry, actually p, right? Because p prime should be equal to 0. So we are going to take actually p to be equal to 1 and w to be equal to 1. So if we do that, we are going to get that the second derivative of psi with respect to x plus q psi for this expression, right? But we know that this is equal to minus lambda psi, okay? And if we take q to be equal to minus 2m of x divided by h bar squared, and lambda to be equal to 2me divided by h bar squared, we can say that this is the second derivative of psi with respect to x squared minus 2mb divided by h bar squared psi equals to minus 2me divided by h bar squared times psi. Okay, so from here, the Sturm-Liouville operator will be the second derivative with respect to x and then plus q, right? From here. But q is equal to minus 2m b of x divided by h bar squared. Again, if we write this as L applied to psi, this is equal to minus lambda psi, where lambda is this thing over here. So this will be the Sturm-Liouville operator for the Schrödinger equation, and this is the Schrödinger equation in terms of the Sturm-Liouville operator. And I think that with this example, I'm going to finish the lesson right now. Remember, the Sturm-Liouville operator is Hermitian. And thank you so much for watching the lesson.